Alright guys, how's it going? This is where we left off yesterday in class. We're going to skip the Kahoot. We'll do that in class tomorrow. We're going to go on to collisions and conservation of momentum. Um, so let's talk about two objects that are colliding with each other, and we'll ignore any other forces like gravity or air resistance. We're just looking at, let's say, two objects that are floating in space and they just happen to be um, on a trajectory that would cause them to collide at some point. So we have two objects, mass 1 traveling with some velocity, mass 2 traveling with some other velocity, and based on their velocities, they're predicted to collide at that point. During the collision, there's going to be a very large force from mass 1 acting on mass 2, and that force will be in the right direction. And there's also going to be a force from mass 2 that's acting on mass 1. That's going to be over towards the left. And those forces, by Newton's third law, have to be equal and opposite to each other. So the magnitude of those two forces is the same. So one way that we could think of this collision is not as a collision between two separate objects, but we could define the system as being both objects. And that means that the action-reaction pair, those two forces, are an internal force to the system. So both forces are internal to the system if we define this system as being both objects. And that's something that we're going to use to be able to exploit momentum conservation. When we're done, the forces that they felt during the collision are going to cause an acceleration. They're going to cause a change in the velocity of each of the objects. And we could also think of this collision as taking place over a certain amount of time. And so the impulse that both of the objects felt will cause a change in their momentum. And individually, the two objects will have a change in momentum that's based on the ratio of their mass. But if we define the total system as being both objects, and so the total momentum is the sum of the momenta, both momentum of each object, then the impulse on the system would be zero, because if the two forces are equal in magnitude but opposite in direction by Newton's third law, then the total impulse of the entire system is zero, and so there can't be a change in momentum. And so that's why it's useful for us during a collision to define the system as both of the objects and not look at one individually. Because those internal forces are action-reaction pairs, and the net impulse is zero during the collision in that case. So let's define conservation of momentum. What does it take for momentum to be conserved? So number one, internal forces. Forces that the objects within the system exert on each other. So we just saw that. If we have a system that's made up of multiple objects, when they collide with each other, they exert forces on each other that are action-reaction pairs by Newton's third law, and they're equal and opposite to each other. So those are defined as internal forces. They're internal to the system. External forces are forces exerted on the objects by agents external to the system. Examples of this would be gravity, friction, an applied force, tension, these are all things that could potentially be outside of the system. They're not forces that the objects exert on each other. They're forces somewhere other that are exerted maybe on both objects or something like that, but they're not internal to the system. So with those two definitions, the principle of conservation of linear momentum says the total linear momentum of an isolated system remains constant, meaning it's conserved. An isolated system is one for which the vector sum of the average external forces acting on the system is zero. So what does that mean? It's telling us that as long as the sum of all the external forces is zero, then the system is isolated. An isolated system is a system where only internal forces are acting, or the net external force is zero. So that's what we're going to be looking for momentum conservation. The net external force needs to be equal to zero, and then the system is isolated, and the momentum would be conserved. So let's look at an example here. So we've got billiard balls on a table that are going to collide with each other. So this example says, imagine two balls colliding on a billiard table that is friction-free. Using the momentum conservation principle as a guide, decide which statement is correct. The total momentum of the system that contains only one of the two balls is the same before and after the collision. B, the total momentum of the system that contains both of the two balls is the same before and after the collision. So this is a nice way of checking whether or not we understand the definition that they just gave us. In this case, the weight and the normal force are external forces. And if we look at each object, the normal force on ball 1 and the weight of ball 1, then the net of that force is zero. And the same is true for ball 2. The normal force is exactly counteracting the weight of the ball. We're assuming that the table's level and the balls are not bouncing on the table or anything like that. That's a pretty reasonable assumption. So in this case, and the table they said was frictionless. So in this case, the only external forces acting on the balls would be the weight and the normal force. Now, if we define the system like they did up here as just one ball, then during the collision we have another force. We have the force of one of the balls on the other during the collision. And this force comes from outside the system because we defined the system as being just one of the balls. So in this case, momentum is not conserved. The momentum initially is not equal to the momentum that we have after the collision because of the way we defined the system. In the second example, you can see they defined the system as both balls. And so in this case, our free body diagram would be both, and those forces are equal and opposite to each other, and they're internal to the system, so they cancel each other out. So in this case, the total momentum of the first ball plus the momentum of the second ball, since our system is both balls, we need to include both, is conserved. And this is an important point. The individual momenta of the ball before and after, maybe the first or the second ball, can change. But the total momentum of the system in a situation like this is conserved. Let's go on to a different example. So here we have two freight trains. Number 2 is going faster than number 1, and eventually it's going to couple with it. So there's going to be a collision, and they're going to get locked together. So if we define the system again as both train cars, then we can use momentum conservation. They tell us to neglect friction, so we're going to ignore that, and the only other external forces we need to worry about would be gravity and the normal force. And since this is rolling on a level surface, we know those are going to cancel each other out. So the net external force acting on the system is 0. There is going to be an internal force during the coupling. When they get locked together, there's going to be a very large force acting on each of the cars from the other car while they get locked together during the collision. And because we define the system as both of the train cars, those forces are internal to the system. They're equal and opposite, so they cancel each other out. So we can set up a momentum conservation equation, and the way that we need to do this on the AP test is we have to start by explicitly saying that momentum is conserved. So we're going to say momentum initial is equal to momentum final. And then we need to write a more explicit statement. So we're going to say momentum 1 initial plus momentum 2 initial is equal to momentum 1 final plus momentum 2 final. And remember that momentum is equal to mass times velocity. They gave us mass 1, they gave us mass 2, they gave us the initial velocity of car 1, and they gave us the initial velocity of car 2. So it looks like the only thing we're missing is the final velocities of both cars, and at first it doesn't seem like we have enough information to solve the problem. But actually, because they get locked together, they're going to travel with a common final velocity, and they say that right there. So we can use that to help us solve the problem. So we're going to write this out. So we're going to have mass 1, velocity initial 1, plus mass 2, velocity initial 2, equals, since they have a common velocity, we'll have mass 1 plus mass 2 equals that common final velocity. And then we can solve, and we'll have mass 1, velocity initial 1, plus mass 2, velocity initial 2, over mass 1 plus mass 2 equals the final velocity. And that would be our answer. Plugging that into a calculator, we get that it is 1.1 meters per second. And what you'll notice is both of the velocities of the train cars changed. So the momentum of each train car before and after the collision changed, but the total momentum of the system is unchanged. And that's why it's important for us to define the system properly.